Okay. So, chemical equations are kind of the shorthand for chemistry. I love it. I'm not a word sort of person, so all in one sort of chemical equation, can you say what chemical reaction is going on? I love it, so we're going to talk about that today. So I think we've talked about this definition before. What is a chemical reaction? Well, I know we talked about it when we talked about chemical properties. So to measure a chemical property, a chemical reaction has to have occurred for it to be a chemical property. So a chemical reaction has occurred if you get new substances. So one of the things we're going to focus on is you get new substances, but you have the same old atoms that are just combined differently. In my other chemistry class, we're talking about the structure of an atom, kind of like we already did in this class. And of course, you guys would tell me the electrons are the outermost. So honestly, when these new substances are formed, it's the electrons that are doing the heavy lifting with regard to forming new substances. All right. So how would you know that a new substance is formed here? We have this liquid in the pipette and this clear liquid here.
Change color.
Just the color change, yep. Anytime you see something kind of, well, we'll be talking more about precipitates in general chemistry too, but there's a good chance you could isolate this with like a centrifuge. It's probably sludgy, it's probably a solid. Well, how about this one? The shape has changed?
Or has it?
I kind of think maybe it is. It looks like there's green slime, but there's a chance that maybe this is kind of eaten off, yeah. So in the color and maybe the gas. Pennies aren't pure copper, but they have a lot of copper in them. And actually, we're going to do this chemical reaction. This is probably nitric acid. Yes, nitric acid. I think it's illegal. Because you're defacing money, you know. So, what do you think? Chemical reaction? How? Why do you think?
It's a chemical reaction.
What's that?
Yeah, because of just the color.
The color, maybe it's
Because
releasing
the electrons
energy.
are probably being excited too. We're going down to a lower energy level.
Mm-hmm.
Is that exploding? What is that doing? Just lighting up?
The caption says we have iron gauze that we're burning, basically. We're burning iron gauze in the presence of oxygen. And, yeah. So those were chemical reactions. New substances were formed. So chemical reactions are shorthand, quick and dirty, written down using chemical equations. And we read chemical equations, especially in Gen Chem 1, from left to right. So we start here with reactants, and we go to products. 1, 2, from left to right. The arrow there is called the reaction arrow. Sometimes, to me, I kind of think of the reaction arrow as being time. Give it some time. How much time? Well, it depends on what we call the reaction kinetics. So I feel like I'm going kind of fast, but let me know. I think we're okay on the same page with all this. So chemical equations can either be unbalanced or balanced. And I'm going to kind of walk you through. Okay, unbalanced, I'll just put it this way. Balanced gives more information. More info. Specifically, it gives info about amounts. I'll put info about relative amounts. AMT for amounts. But I want to start with the unbalanced equation. So an unbalanced equation will show what you're starting with, that's your reactants, and they will show then the reaction arrow, and on the right of the reaction arrow is what you end with. And we call what you end with products. Read them from left to right. Reaction arrow separates the reactants and the products. And then we have some options here with regard to the author of your chemical equation. So whoever wrote the equation sometimes can choose to indicate what the physical phase of the species was. The physical phase being, of course, solid, liquid, gas. Then the author may or may not wish to add another piece of nice, neat information, or it could be a series of types of things. Over the reaction arrow, they might want to just kind of jot down what conditions are required for the reaction to proceed. So sometimes it's heat, sometimes it's light, sometimes it's the absence of light, sometimes it's a specific temperature, sometimes it's a minimum temperature, sometimes it's a maximum temperature, but all that stuff can be over the reaction arrow. So it's kind of nice. With regard to physical phases, of course, we have solid, liquid, and gas, the physical phase of your reactant or product. And I'm going to throw up AQ there. AQ, like the caption says, means that it's dissolved in water. So your lab tomorrow, we're going to be dealing with NaHCO3, that's sodium bicarbonate. You're going to take solid and dissolve it in water, and it's going to be AQ. Now, I don't know how to quite describe this. We'll be talking more about, this is an ionic compound. That is something we talked about before. We said an ionic compound, I said look for the metal. What is a metal up here? Which element's a metal? Na. Yep, there's your metal. It's an ionic compound. Let me go ahead and kind of tell you how this thing breaks then. This thing breaks right after the Na. And then we have HCO3. Okay, so this thing actually ionizes or breaks apart into Na plus and HCO3 minus. So my whole point is, in that beaker of where you have dissolved sodium bicarbonate, you have Na plus and HCO3s minuses running around. That's all aqueous means, bottom line. All right, so I mentioned that the author may or may not want to tell you kind of concisely over the reaction arrow conditions you need in place in order for it to react. That's kind of nice. Concise. Concise is good. So all of that stuff that I've talked about with an unbalanced equation is what we call qualitative. Qualitative, the quality of the reaction. The reactants, the products, the physical phases. It's not quantitative. Quantity, quantitative. So if we kind of up the ante a little bit, we can actually take a chemical equation that has reactants and products, and we do a process called balancing, and we'll talk about, you probably run into this before. We can actually balance both sides of the reaction arrow, okay? And then once we're done, we have a balanced equation. And balanced equation gives us quantitative information. I tell students a balanced equation to me is kind of like a recipe. It actually tells you, not, if you're going to make brownies, what do you need? Oh, butter, flour, sugar. Well, how much? Okay, so that's where your balanced equation comes in. Okay. Whoops, sorry. So this says then a balanced equation gives you both qualitative information and quantitative information. So in this process of balancing, what we need to end up with is this. We need to end up with, basically on either side of the reaction arrow, we need to have the same number of atoms of each type of element on either side of the arrow. What you start with, the atoms that you start with, they're going to be arranged differently, but need to be the atoms that you're left with. So, for example, down here at the bottom, you see the chemical reaction. NO plus O2, those would be, and we use just the letter R for reactants. So here we have the R's, okay, and here we have the P. Now, notice that I'm going to just kind of act like this is new to everybody, because you may have run into it before, but just bear with me. This number 2 here actually is what somebody added to in front of the NO to balance this puppy. Notice that there's a 2 over here. That's the balancing part. So if we look graphically, what this means is we have 2 NO molecules, they're up here, plus 1 O2 molecule. The little, I think this is so cool, it's just me. But these little bonds right here, where I've drawn the dash, okay, those are chemical bonds, CHM bonds. Okay, I think of them as basically being broken. And what is formed now is NO2. So those bonds are broken and new bonds are formed. And in general chemistry, too, we'll kind of look a little bit behind the scenes at mechanisms, kind of stepwise, how that happens. But the point here, as far as balancing, so of course you probably are on track with this. This 2 is this 2, and these 2 units is that. And if we were to tally them up, and this is how we're going to balance equations, we go N is equal to O is equal to, on the reactant side, product side, N is equal to, O is equal to. So let's see, what did we say? The blue ones are the nitrogens. So I got, what, 2 nitrogens over here and 6 oxygens over here. And looks like I got 2 nitrogens over here. Oh, and 4 oxygens over here. Looks like I miscounted. Wait, no? Yeah, okay. 1, 2, 3, 4, final answer. So we're good. That's the balancing part of it. If I can count. Now I think I've got these videos queued, or will work. Let's see. Yeah, the video that didn't work. Well, can't describe it. But while we have this up here, look at the top there, and we could do a little tally. I call this my brick wall that separates the reactants from the products, and I could count phosphoruses and chlorines. Let's see if I can do this right this time. I got 4 phosphoruses, and don't let this throw you off. I have 6 units of 2 CLs. So, yep, I'm looking at 12. So over here, looks like I've got 4 units of PCl3. That gives me, what, 4 Ps? And it gives me 12 CLs. We're going to call these in a minute stoichiometric coefficients. So the 6 and the 4. So what is the number here in front of the P4? It's 1, exactly. Yep. Those are called stoichiometric coefficients. I'll just put COEFF for coefficients. Yep, the 1, 6, and 4 stoichiometric coefficients. Yep. Very good. So this is just a still image of what you saw. I think this is a neat reaction. I like its exothermic. Releases a lot of energy in the form of light and heat. And I also like it because the L, of course, means liquid. I like that you get something different. You have a solid and a gas, and you get a liquid out of it. Who would have thunk? So this might look familiar. You guys did this reaction, chemical reaction, between magnesium and you burned it with oxygen in the air. And does it seem like this is balanced? Let's just go ahead and do it. Here's my brick wall. I have magnesiums and oxygen to count. And what, we got 2 magnesiums and 2 oxygens. On the reactant side, on the product side, we're looking at 2 and 2 also. Wonderful. So what's the stoichiometric coefficient for MgO? It is 2. Yep. Coefficient for O2? Coefficient of 1. Yep.
What was the first question?
What was the stoichiometric coefficient of MgO? Yeah, it is 2. And do you see where they're like a recipe? I mean, they say like how many, like your ingredients would be your reactants and your product would be like what you make and eat. Let's try this one.
I've enjoyed our little labs.
Good.
I don't like so much writing about them, but I
Fair.
enjoy doing them.
Fair enough. And no one's burned anything down yet. That's good. That's a good thing. So we're going to talk about balancing, okay? And when we balance an unbalanced equation and we go to balance it, what we're going to do is basically play with those stoichiometric coefficients. By default, they're 1, but we need to kind of change them around so that we have the same numbers of atoms of each type of element on both sides of the reaction arrow. Okay. All right. So there are actually at least a couple ways of coming up with that. I call it a set of stoichiometric coefficients. A set of stoichiometric coefficients. There's at least a couple ways of balancing equations. And we're going to do it by trial and error or just simply by inspection. So this is where, for your next unit exam, if you're one that likes to use a pen, which is great, you might want to bring along a pencil just for this part. Because yeah. And it's not because we do anything wrong as we do this process. It's just that we erase it and we up it. You'll see what I mean. We just kind of increase the amount it's by inspection or trial and error. First off, thou shalt not make new chemistry. So that means that your reactants you start with and your products you end with are it. So the formulas you're given, you can't mess with it. And to mess with the subscripts would be to mess with a formula. So, I mean, a good example would be like if you have H2O, let's see, is this a good example? Oh yeah, this will work. Okay, and we're going to run electricity through it, and we're going to break it down into hydrogen gas and oxygen gas. That's great. Okay, that is your chemical reaction. You're like, I know how I could balance that. I will just change this 2 into a 1. You're playing chemistry. Okay, you cannot do that. Okay. But instead, and let's just go ahead and do this, what I do, those black squiggly marks are where I can put a stoichiometric coefficient. Okay? So that's how I start, and then I kind of go back and forth. I better put this back as a 2, like it should be. So what I usually do is, what do I usually do? I probably would recognize, like, I leave these guys till last. I leave my guys that are by themselves. That line, I just leave it till last. I'm going to actually start by balancing. I'm going to start with this guy because he looks more complicated. So do you see where, so how can I get 2 oxygens with H2O? I can put a 2 there. Yep, I'll choose purple. So if I put a 2 there, oxygen, oops, sorry. Hydrogen equals, oxygen equals, hydrogen equals, oxygen equals. So before the 2, my hydrogens were 2, my oxygens were 1. And I have 2 and 2 over here. And you told me to put a 2 there. And now how many hydrogens do I have?
4.
I have 4. And how many oxygens do I have?
2.
I have 2. Okay, that's great. So now the only thing I need to fix are my hydrogens. Okay, so I have 4 hydrogens on the reactant side. How do I get 4 hydrogens on the product side? I'll put a 2 there. And when I put a coefficient there, I update my quantities. So all I need to do is update my hydrogens from 2 2, 4. And that's balanced. That's it. So I say the set of stoichiometric coefficients is 2, 2, and 1. That's my set of coefficients. So thou shalt not change subscripts. But, but what you shall do is do what we just did. That black squiggly line to the left of the species, that's where you're going to do your work. Okay, those are called stoichiometric coefficients. Oh, and then this is something that I think we've already kind of seen this afternoon. It's just when you have, and I call it the big number to the left, the stoichiometric coefficient is the big number to the left. Whatever that number is, it applies to the whole thing, enchilada. Okay, so let's do one. And I'll kind of do like I did with my water. So I'll draw my brick wall. I'll do my tally. I have FEs, I have H's, and I have O's. FEs, H's, and O's. And I'll write down what I'm starting with. So with coefficients of 1, I got 1 iron, 2 hydrogens, 1 oxygen. I have a whopping 3 irons over here. Yeah, 3 irons, 2 hydrogens, and 4 oxygens. Cool. I'm going to put a star next to the ones I'm going to leave till last. I'm going to leave my H2 till last, and I'm going to leave my Fe till last. One last thing I'm going to do is to put my squiggly lines where my coefficients are. Squiggly line in front of the Fe, squiggly line in front of the H2O, squiggly line Fe3O4, squiggly line H2. All right then, cup of coffee. I probably would focus maybe on my oxygens, because I'm like, dude, I've got 4 oxygens over here. I know I got to get 4 over there. So how can I fix my oxygens? Yep. Did you say multiply it by 4? Yep. So I'm going to put a coefficient of a 4 up here in front of my H2O. And then I need to update my quantities. So that didn't change the iron, but it changes the hydrogen. How many hydrogens do we have now? Yep. And then how many oxygens do we have?
4.
4, which is what we wanted. Sometimes I fix something and then it gets messed up later. So it's fixed for now. Cool. Well, that leaves my hydrogens and my irons. Wait. Yeah, okay. So my hydrogens I'm going to fix next. Okay, I've got 8 over here and I've got 2 over there. How do I get 8 on the product side? Multiply by 4, yep. So I'm going to put a 4 here and I need to update my hydrogens. So, yep, that gave me 8, didn't it? Cool. Now my hydrogens are great. Then all I need to do is fix my irons. So I have 3 irons on the product side, and how do I get 3 irons on the reactant side? Multiply it by 3, stoichiometric coefficient of 3. That's exactly it. And update my iron quantity. Now I got 3. But like I said, sometimes you'll fix something and it'll mess something else up. You just kind of have to go back and forth. That's it. And so I say my set of stoichiometric coefficients are 3, 4, 1, and 4. That's the set. That's my recipe. Recipe is 3 and 4, and what do they make? 1 and 4. Any questions about that? I'm going to do a couple more. Kind of different nuances. And actually, I'm going to have that last slide, and then we'll be done when we finish this part. That last slide is a homework slide, and I'm going to show you on the internet where actually you can just plug in, like in the internet, we can plug in Fe plus H2O equals Fe3O4 plus H2 on the internet, and it will tell you what the balanced equation is. It's a program. Like, yay!
I like this program.
Yeah. Okay, so there's your check. It all looks good. I don't know if you have to fill in anything. Okay, good. Now this one is, once we talk about ionic compounds and what we call polyatomic ions, this will maybe make more sense. But I want to tell you, I'm going to go ahead and make my tally. Of course, we have R's and P's, reactants and products. And I am going to keep the SO4 together because I have 3 of them. And I'm actually going to keep my OHs together. And I'll show you what this looks like. You wouldn't have to do this. If you broke it up into atoms, it would still do the same thing. But doing this way, I have aluminums I need to account for. I have SO4s I need to account for. I have NAs I need to account for. I know I'm ignoring charge, but just bear with me. And I have OHs I need to account for. I'm just going to go ahead and write them once over here on the left, and I think we're probably okay with thinking of them as also being on the right for the products. So if I go with coefficients, oh, where's my squiggly line? Here's my squiggly lines. This is this is my stoichiometric coefficient where it will go. If I go with coefficients of 1 across the board, it looks like aluminum, I have what, 2? Units of SO4s, I have 3. Sodiums, I have 1. OHs, or OH minuses, I also just have 1. Then on the product side, aluminums, I have 1. SO4s, I have 1. Sodiums, I have 2. And OHs, I have a whopping 3.
Question. It says SO4 and then it has the 3. Are we just ignoring the 3?
So the SO4, and it has a 3 out there, that's why I put a 3 here. I have 3 SO4s.
Oh, got it.
Yep. So no, you're right, we cannot ignore it. And I did the same thing for OH over here. I have 3 of them. So, let's see. Let's fix our OHs first, if that's okay with you. So our OHs are down here at the bottom. I have 3 over here on the product side. To get 3 over here on the reactant side, I need to change that 1 to a 3. So here I go. This is now 3 in front of my NaOH. I need to update my Na. Now I have 3. And update my OH. Now I have also 3. So my OHs are balanced. So far, so good. Now I'm going to go ahead and balance my sulfates, if that's okay with you. So my sulfates, well, my SO4s. I'm going to balance my SO4s. So it looks like I have 3 over here. If I want to get 3 over here, I can do that if I put a 3 in front of the Na2 SO4. So there's a 3 there. I need to update my NAs. So now I've got what, 6? Okay. And the SO4s, I've got 3, which is what I wanted.
That's not gonna work for you.
I know. I'm not done yet. This is while it's trial and error, and this is why I use a pencil. So, it looks like I still have a couple of issues, like Joshua said. My aluminums, I got 2 and 1, and my sodiums, I got 3 and 6. Are you serious? Well, let's try fixing our aluminums. Okay? This is going back and forth. You see how I'm going back and forth? Let's fix our aluminums. I have 2 here. If I want to get 2 over there, I need to put a 2 in front of my first thing there. So 2 in front of the AlOH quantity 3. Update my aluminums. Now I've got 2. That looks good. Okay. And then update my OH minuses. So now I've got, what, 6 of those things, don't I? Does that make sense? Okay. So now I have officially unbalanced my OHs. Right? Okay, but how else are we doing? We're doing my aluminums match, my sulfates match, my sodiums, and my OHs don't match. Well, let's go back up to our sodiums and see if we can get them to match. So we have 3 sodiums on this side and 6 sodiums on this side. So we can get 6 over here if we change that 3 to a 6. What color do I want? So I'm going to change this to a 6. Now let's see what I got. So I need to update my NAs. Now my NAs are 6, and my OH, or H minuses, are also 6. Does that look okay? According to my math, I'm good. What do you think? So we balance 2 aluminums, 3 SO4s, 6 NAs, and 6 OH. So my set of stoichiometric coefficients are 1, 6, 2, and 3. Any questions about that? Now, if you'd broken them up into individual sulfur and oxygen atoms for the SO4 and oxygen and hydrogen for the OH, that'd be the same thing. But it's definitely a back and forth. It's not linear. That's what I think. Okay, so this check works. This is the way we did it, and this check, or the other check, would work too. Okay. So remember I put a star next to a few things, like a star next to the Fe or a star next to the H2. Those were things that were in their uncombined elemental forms. They were not combined with any other element. Okay? So save them till last. So let's do one more. So speaking of save till last, so let me put a little asterisk next to the only thing, what's in its uncombined elemental form up here? The O2, yep. So I'll put a little asterisk there. I'm going to save him. I'm going to put my little squiggly marks. There's where I can put a number. I'll draw my brick wall. And then on either side of the brick wall, I'm going to draw carbon equals hydrogen equals oxygen equals. Okay, so with coefficients of 1, it's looking like what? I have 4 carbons, 10 hydrogens, and 2 oxygens. Now on the product side, we have 1 carbon. Now here's where our hydrogen is 2 hydrogens. Here's where we need to actually add the oxygen from both of the products. So we would have 3 oxygens. All right, time for a cup of coffee. I think what makes sense to me is to go for my carbons first. You could go for hydrogens, but I just usually go for carbons. Be about the same thing. So I have 4 carbons over here on the reactant side. How do I get 4 carbons on the product side?
Multiply by 4.
Yep, multiply by 4. Change that 1 coefficient to a 4. So we update our carbon as 4, and then we have, well, right there, oxygen-wise, now we have, instead of 2, we have 8, and we have 1 oxygen over there, so I'm getting 9. Does that seem right? 9 oxygens. So update those. Cool. Well, then I would probably, just how I am, go ahead and try to fix my hydrogens. So I have 10 hydrogens over here. How do I get 10 hydrogens on the product side? Yes, change it to 5. That's right. So we put a 5 in front of the H2O, multiply H2O by 5. So now that gives us, what, 10 hydrogens. So by my count, I should have put check mark in front of the carbon and check mark in front of hydrogen. By my count, those two are balanced. Let's see, we need to update our oxygens, don't we, since we put a 5 there. So Looks like I have 8 plus 5 or 13. So instead of 9, now I've got 13 oxygens. So we have two choices here, and I'm going to show you how I would do it. The problem is we have oxygens that come in an even set of 2, and we need 13. Okay, so you're like, well, how are we going to do that? Well, and we'll talk more about this Friday. But if we recognize those coefficients as being relative numbers of moles, not molecules, this is how I think of it. I think of basically, there's my O2 here's my O2 molecule. So if I want 13 oxygen atoms from molecules, if I were able to, and you're not supposed to be able to, but if I were to be able to basically break that, sever that, okay, if I went with 13 halves O2s, what does that do for me? 13 halves. So here's my O2, and I'm going to take 13 of these individual halves. You're going to have 13 oxygen atoms. 13 halves of O2s gives you 13 individual atoms. I'm seeing I'm not convincing you guys.
It just seems like you changed the subscript a lot.
It does seem like that, but we're going to actually switch gears, and instead of going on a small scale, we're going to scale it up to moles here in a short amount of time. And you can have a fraction of a mole, but you can't have a fraction of a molecule.
That's
So,
pretty cool.
yeah. You can have a fraction of a mole.
So you write that just 13/2 O2.
Because if I do that, and if you buy that, if you're okay with this, then actually what I've done by putting a 13 halves there is change this from a 2 to 13 oxygen atoms. So now my set of coefficients are 1, 13 halves, 4, and 5.
We could only do that since it was an O2, since there wasn't a coefficient.
You can only do that because you can think of a half of an O2 molecule. That's the way I think of it.
If there would have been some other coefficient there, do we ever have those? Or is it just when it's?
That's a good question, and I don't know if this was your question, but if you had Br2, you could have a half of that. Iodine is notorious for coming in triples. You could have a third of that.
But there is not a number in front of any of those. It is just simply
Right.
it by itself.
Yeah, right. You could not have a half, I don't think, of a CO molecule. Not in this context of balancing it to try to get the same number of atoms of each type of element on either side of the. You can, but not right now. And actually, we will have half a moles of. Now, if this bothers people, and this might help you, Joshua, because I don't like that. I don't like the fractional. But do you know how you scale up? If you wanted to make, if you knew a recipe would make a dozen cookies, and you wanted to make 5 dozen cookies, you would just take all your ingredients times 5. And that's exactly what we can do here. So we can go ahead and multiply by 2, multiply everything by 2, and you'll end up with this. So all we did was scale up everything. So we scaled up our ingredients, and it also scaled up what we got our product-wise.
How would you want the final answer? If we
Either
went
way.
with the first one, it'd be okay.
Either way, yep. Either one's great. It's all about relative amounts, and these actually are saying the same information. This is just making one batch, and this is making 2 batches. but there's all balanced. And every once in a while, I'll have students that will, for whatever reason, end up, we could take this times 3. We could take 2, 13, 8, and 10 times 3, and we would get a third set down here. That would be fine too. We're just scaling it. So, they work, it all works both ways. So, this is my, kind of what I've been saying, the 1/2 O2, I know it seems like that I just went and I changed the subscript from a 2 to a 1 and kind of thought it through, and you can't do that. But the fractional coefficients are okay if you think in terms of moles of molecules, not molecules. Okay, so sometimes, now you guys are thinking ahead probably to the next unit exam, right? So my definitions, this is a favorite, stoichiometry. I just love the word stoichiometry. So what you've done when you balance an equation is basically given the recipe, you've given the relative amounts of what you start with and what you end with. Those were the stoichiometric coefficients, so that's the stoichiometry of the chemical reaction. So these are going to be due on Friday, Fabulous Friday, and I am going to take you out, I think, to this website. I'll link to this website on Twitter, but you can jot it down if you want to. It's www.webqc.org. Sometimes students might, you might ask, when I do these, Mrs. Snipes, do you need to see the work, like the tally, the reactants and products? No, not necessarily. But I just need to, sometimes students will like draw a box around their stoichiometric coefficients, which is kind of nice. So I'm like, oh, there's your stoichiometric coefficient. So let's see if this works. I've got it plugged in, so it should. But I bet it's gonna. It did, so hold that thought. I just need to click this. So the site I gave you, and like I said, I'll push it out there on Twitter, looks like this. It's kind of weird, doesn't it? If I could have some helpful, this is why we do not have open book tests or open notes or open internet tests. So this is, did you guys see where I went to? I went to online tools. So go to online tools up there in the upper left. And right here you see chemical equation balancer. And so actually I jotted down your first one. Okay, so we'll go ahead and do the first one up there in the box. It's waiting for you to put some information. So I'm going to put SO3. Notice there's no subscript, so I'll just put capital S, capital O, 3. I'll put equals for the reaction arrow. I can't believe I'm showing you guys how to cheat like this. SO2, and then we have another product, plus O2. This is so cool, so fun. And if I click balance, okay, there it goes. Stoichiometric coefficients of 2, 2, and 1 respectively. Right? So I just did the first one for you. But wait, there's more. If I scroll down here, okay, actually in tomorrow's lab we'll be talking about how you use balanced, tomorrow's lab is a little bit ahead of lecture. So tomorrow's lab, we're just going to collect data. I'll talk a little bit about kind of the conservation of matter. But to do the calculation for tomorrow's lab, you're going to probably have to wait till Friday's lecture. But I'm telling you, in Friday's lecture, these are really nice. You guys have been doing molar masses. So what somebody did is go to the periodic table, look up for sulfur, plus 3 times oxygen, and came up with 80.0, whatever that is, 80.0632. And the cool thing here is if you had a weight of 12 grams, I didn't do this in my office, 12.3 grams. This is so cool. So I put 12.3 grams of SO3 in there. Notice it told me the moles, and then it also told me what we're going to form on the product side with regard to, we had 2 products. We had the SO2 and the O2 product. And this is just wonderful. This is what we call stoichiometric calculations. And again, this is actually the crux of what you're doing in tomorrow's lab. We'll be talking about it in lecture. But isn't that nice? All right. So that's all I have for today. And then we have a study session, but it sounds like everybody's on tracks. But I'll be over there